In this part of the video, I'll explain some other tests. To start with, an explanation about grommet testing that we have done earlier. On the left-hand side, you see a picture, and in that picture, this is actually the video screen that looks into the test machine, into the test bed. We did grommets testing, grommet being an endless steel wire rope sling. In the video, you see how the grommet is put under load and up to breakage. We did this testing with newer grommets, older grommets, newer shackles, older shackles, and this is just an example of the test result. On the left-hand side, the shackle pin, yes, it has bent a little, but recognize that this is a 150-ton shackle with a brake load of 750 tons after the test load of 637 tons. So it has a little deformation as to be expected, but still could be dismantled from the shackle body. The middle picture is the deformation in the shackle body after such a high load. And on the right hand side, you see the picture in which we brought the steel wire rope to failure. In the next part, I'll explain a little bit about synthetic round sling testing. We used a test machine that has a capacity of 600 tons. This test was done with span-set round slings. The testing is about the performance of these round slings in combination with green pin shackles, and especially about D/D ratio. The next section explains about Sharpie V testing. The Sharpie V testing is about testing ductility of a material at a certain temperature. We do that by taking a test piece, a test bar, out of the material and machine it to certain specifications. This is the test bar that is in the test machine. This piece is put in an anvil here at the bottom. And we have a hammer in this part, and the hammer is lifted to a certain position and then dropped. That hammer hits the test piece with a certain speed. Depending on the toughness of the material, that test bar will break and take energy from the hammer. The hammer will continue to swing until a certain position. If the test bar takes a lot of energy from the hammer will stop already quite quickly, and you can actually see on the scale a high reading for the Sharpie V result. If the material is not that ductile and breaks very easily, the end of the swing will be quite high, resulting in a low value for Sharpie V. On the next slide, you see the actual machine, live scale, and you can see it's quite a big machine. These are some of the results. In the bottom, you see the test bar before the test. Then in the middle, we see an example of a bar that broke, wasn't very ductile, it broke easily, a low Sharpie V value. The top of the picture, you see a bar that was quite ductile. It didn't break that easily, it had a high Sharpie V value. There is requirements in the standards. The European standard requires 27 joules at -20. There's also a requirement from DNV-GL. The requirement for offshore lifting appliances is 42 joules at design temperature. Of course, we make sure that our products meet these specifications, as you can find them in the Green Pin catalog. The next section is about NPI testing. NPI testing is done to make sure that there are no cracks in the material or near the surface of the material. On the right hand side you see an example of a test bar, and the lines in the test bar are actually magnetic flux lines. How does the process work? NPI stands for magnetic particle inspection. So the process works as follows. The test bar is put in the test machine and an electric field is used to induce a magnetic field in the test bar. That magnetic field induces magnetic flux lines through the material. If there is a discontinuity in the material, it shows up on the surface. On the surface there is used a special liquid that has small iron particles, and that liquid actually makes sure that it is showing up under UV light, those magnetic particles. Advantages of magnetic particle inspection are that it's easy to find surface and subsurface defects, and it gives actually quite rapid results. The indications are visible to the inspector that does the testing. It even can detect small defects that have been smeared over in the forging process. Here's a video about NPI testing.
Non-destructive testing. Magnetic particle inspection. The magnetic particle examination is an excellent method to investigate near-surface defects in ferromagnetic materials. This video shows the basic principle and the practical procedure. The material tester gets the machine ready for use and inserts the test piece between the two poles of an electromagnet. Then she takes a bottle with a suspension of magnetic particles, turns on the electromagnet with a foot switch and applies the suspension of magnetic particles onto the test piece. Already in daylight, dark lines are visible on the surface. The lines can be seen much better under ultraviolet light, and particularly well at darkening the daylight. The suspension contains pigments that cover the magnetic particles and fluoresce under ultraviolet light. The particles run off in areas free from defects, and they are attracted and clustered near defects. This workpiece shows a whole array of cracks. The basic principle is to magnetize a ferromagnetic workpiece parallel to its surface, as shown in the sectional view. If the workpiece is free from defects, the magnetic field lines run within the workpiece and parallel to its surface. In places of magnetic inhomogeneity, for instance near cracks, the magnetic field lines will locally leave the surface and a leakage field occurs. Now, if a suspension of ferromagnetic particles is applied onto the test piece surface, the magnetic particles will run off at defect-free areas. In places of leakage fields, the magnetic particles are attracted and clustered together, thus indicating the place of the defect. The method works best using a pigment which covers the magnetic particles and shows fluorescence under ultraviolet light. Even cracks can be detected that are not open to the surface but just below it, as long as they are not too far below the surface. But one precondition must always be fulfilled. The magnetic field lines must be perpendicular, or at least at a certain angle to the defect. Otherwise there will be no leakage field and the defects remain undetected. Our test sample has been magnetized in horizontal direction. The magnetic field lines run horizontally. This is the reason why cracks in vertical direction are visible particularly well. To make sure to detect all near-surface cracks, one has to magnetize the sample once more and best perpendicularly to the first time.